Okay, I wanted to give a little bit more detail on energetic cost of locomotion, in particular, the relationship between VO2 rate and stride frequency. Now, I could also do VO2 and stride length. And what's important to recognize is this relationship is at a fixed speed. Okay, it's often a subtle detail that is not really considered when looking at some of these data. But what I presented before is the classic relationship of stride frequency on the x-axis and rate of oxygen consumption on the y-axis. Again, the dot representing a rate. And what I drew was we would have someone run and we would put their preferred stride frequency right here at the middle of the plot, and then we'd measure VO2. And then we would have them run with a faster, maybe 10% and 20%. And I talked about this being a really large change in stride frequency, but nevertheless, this is the typical experimental model to do something like this. Sometimes people do 5, 10, 15, 20, plus or minus those changes. And in general, we expect VO2 to increase with changes in stride frequency. And again, this is probably more of a J phenomena where it probably increases a little bit more on faster stride frequencies than on slower stride frequencies. Now I could do this same plot with stride length, and I'll just put it down here as a secondary. This could be PSL. I could put stride length on the x-axis, and then this is just flipped. This would be minus 10% preferred stride length, minus 20% preferred stride length, and plus 10% and plus 20%. Because we know the product of stride frequency and stride length is equal to velocity, and velocity is fixed. Oh, excuse me. All right, so that's one thing to know, is that when you're reading the literature, sometimes you'll see stride frequency on the x-axis, and sometimes you'll see stride length on the x-axis. It doesn't really matter. Of course, the J would be flipped if we flipped this axis to be minus 20%, minus 10%, PSL plus 20, and then this would also be flipped. So just watch your literature, and when you're reading, and double check when they're doing this VO2 running kinematic relationship, what parameter they're putting on the x-axis. Okay. The other part that I wanted to touch on is in this plot, in essence, normalizing the stride frequency data to preferred stride frequency. And I'm calling preferred stride frequency 100%. In reality, we do the data processing a little bit different when we're trying to identify which stride frequency would be the most optimal stride frequency. All right, so let me show that. So I'll write out optimal, and I'll put in quotes stride frequency. And by optimal, whenever we use this term, we have to be really careful, and we need to make sure that we define what we mean by optimal. In this case, and in most cases, optimal means you're looking at a parameter that's neither maximized nor minimized. And you're trying to find where that parameter is maximized or minimized. So either maximal or minimal, or it may be neither, okay? And I know that gets confusing, but this is why we need to be careful when we're using this term optimal, okay? Sometimes it's neither maximal nor minimal, and sometimes it's one or the other. And so I try to be careful in using this term, just like I try to be careful with using terms like efficiency. In this case, what we're going to be looking for is where VO2 as a rate is minimized. Okay. All right. So now let's look at how we would do that. We do the same experiment I've already described, but instead of putting preferred stride frequency here, and this could be stride frequency, and this is going to be VO2, rate of oxygen consumption. Instead of putting preferred stride frequency, I'm actually going to have values here. All right. So whatever units I'm using for stride frequency, whether it be hertz or strides per minute, hertz is technically the best way to do it because we use those in our equation, stride frequency times stride length, and that represents strides per second. If I'm publishing in some literature, I'll tend to use strides per minute because people recognize strides per minute a little bit better than recognizing hertz. So a typical stride frequency for running would be 80 strides per minute. Like if I had you run in a lab, you would probably run at about 80 strides per minute. Well, that turns out to be about 1.3 hertz. So if we take that 1.3 hertz, we may have a maximum number over here of 2 and a minimum number of maybe something like 1, or well, we could do 1. Oh, my divisions aren't going to be that great here, but I can make this scale so that all stride frequencies that I'm going to manipulate are going to be somewhere between these numbers. And then I bring in a subject and they do the experiment I mentioned and I measure their stride frequency. In this case, maybe their preferred stride frequency, or self-selected stride frequency, ends up being right here, and that's the VO2 for that value. And then for this person, we would maybe do minus 5% and plus 5%, minus 5%, minus 10%, minus 20%, whatever we're doing here as our experimental model. And then we do the same thing on the plus side. So now these are not lining up for percentages of stride frequencies, they actually line up to actual stride frequency. And what I do in the experiment is I give the subject this rate to match. So I use a metronome and I try to help them stay on beat with that metronome. All right, once we have those data points, what we actually do at that point, I'll use a different pen here just so you can see it, is we then fit the data with a second order polynomial. Try to do this like that. And that means that the data may not, or the second order polynomial may not pass through the actual data points. Okay. And the second order polynomial you're familiar with because you know projectile motion. And projectile motion is a parabola. And it has a very predictable path using the equations of constant acceleration. In this case, we would do SI or SF equals SI plus VIT plus 1/2 AT squared. All right, that's an equation you should be familiar with. This is a second order polynomial. Second order, so time, or whatever's on the x-axis, is raised to the second power. The neat thing about this math equation is that this has a single point in projectile motion, which ends up being the maximum. All right. Well, when we fit the data with a second order polynomial, there will be a minimum in this case. And what we do is we identify that minimum. And the way I've drawn this, that minimum is occurring right around PSF. And so in this case, I would say this subject is running at the optimal stride frequency, the minimum VO2, given all these other stride frequencies that we used. Now, let's say another subject comes in and runs with a PSF of something, and I'll use a different symbol like that. and then maybe we have another data point here and another data point over here. And maybe on the plus side, they're doing something a little different like that. Okay, so I've got circles here and I've got X's for the other stuff. So this is just another subject. And then let's fit those data with a second order polynomial. And I'll exaggerate here for purposes of this. And maybe it looks like something like that. Now, this is this dot represents this person's PSF. And the minimum for this person is happening right here. I should have drawn that with a different symbol. Okay, just where I drew it, it's lining up with that subject, but it doesn't have to be. Okay, but now what I have is actual data points of someone running, and then fitting the data with a second order polynomial, finding that minimum, and then what I do is I figure out what that optimal stride frequency should be, SF optimal versus PSF for this subject. And then I look at the data and I say, you know what, you as the runner, you are not running at your optimal stride frequency. You need to be 2% faster stride frequency, and then your VO2 should be lower. All right. That's the essence of this test when you're starting to work with runners, is you're identifying their preferred stride frequency. You're identifying other rates of oxygen consumption for other stride frequencies. You're fitting the data with a second order polynomial, and then you're identifying where that minimum of that second order polynomial occurs, and then you're comparing where that minimum occurs versus where the person's actually running. And then you're looking to see if it's the same, like in the first subject I drew, those two ended up being the same point, the same stride frequency. In the second data set I drew, the data sets are, the preferred stride frequency is not the same as the optimal stride frequency. So in this case, recommendation may be to the runner to use a faster stride frequency. And now the key to remember is this is a fixed running speed. So by using that faster stride frequency, that's not saying that they are going to run faster. What that's saying is they would use less rate of oxygen consumption to run that speed if they ran with that faster stride frequency. So they're still running the same speed. How would that translate to performance? Well, performance may be that they want to run further. And then this all sort of makes sense. If they're trying to run faster, well, then I would actually use an even different model than this. But that's where some of the subtleties of this experiment get lost when people, and the research is very rich with identifying the difference between PSF and optimal stride frequency, then identifying the difference in VO2, and then using that to state that if they ran at this stride frequency, they would run X minutes faster for a marathon. That's technically not what this model is showing, okay? That's not. What that model is then doing is extrapolating this difference over to the VO2 speed relationship. And then saying, okay, well, if you're able to run with a faster stride frequency or lower VO2, well, then that means that they could run at that higher VO2, which would mean that they would then be running faster. So it's a jump, okay? It's a jump. It's inferring from this fixed running speed that they may be able to run faster if they run at that new stride frequency. But that's not what this experiment actually shows. So you got to be careful when you're reading the literature on this topic, and first take the data for face value in terms of the experiment is to identify the optimal stride frequency. And then remember that this experiment is based upon a fixed running speed. Now, I'll also say that this change in VO2 or this difference in VO2 is usually pretty small, usually less than 5%. And that's the other point that I made in the other video is we need to start looking at whether or not a small change in VO2, maybe 1 to 2 mLs per kg per minute, ends up being a meaningful difference for a subject. And this cuts back to the type of person, type of athlete you're working with. If you're working with someone who is just trying to complete a marathon, that's probably a different conversation. And we're probably not interested in the subtle details of a 1% or 2% change in stride frequency. But if I'm working with someone who's trying to, hit the Olympic trials, maybe trying to get to a 2:15 marathon, well, now maybe this becomes really important. And that 1% difference may actually be meaningful. So the context of the type of subject you're working with here ends up coming back into play when you're interpreting these data and deciding what to do with it. Okay, so hopefully that helps with this model, and this is just an extension of using a different set of units on the x-axis and then identifying for an individual their optimal stride frequency. And ultimately, what I would do if I'm presenting these data in a graph, I would normalize these data so that PSF always ends up being at the same point, which would then give me this plot right here, where that is 100% preferred stride frequency. And then I align every subject's individual stride frequency. Okay, hope that helps. Thanks.